One thing to notice about the last example that we talked about is there's nothing that says this integral should be fishy at all, which makes it even more fishy. How do we know that we have to do anything special with this integral? Everything looks so familiar. But we have to always, whenever we do an integral, we have to consider the integrand and decide, is there anything special about this with respect to these limits of integration that I need to watch out for? And it turns out it's not just about these endpoints. It could be something happening in the middle of this interval. Take, for example, the integral from 1 to 3 of 1 over x minus 2 quantity squared. Let's work it out as if there's no issue to think about. What's the antiderivative of 1 over x minus 2 quantity squared? Well, it's just straight up power rule. If I add 1 to the exponent of negative 2 and divide by that new exponent, I'm going to have negative 1 over x minus 2, and I'm going to plug in 1 to 3, which means I'll get negative 1 over 3 minus 2 minus negative 1 over 1 minus 2. That gives me negative 1 over 1 plus 1 over negative 1, which ends up being negative 2. If you take a look at the graph of this function from 1 to 3, you should notice that we have everything above the x-axis, and an integral is supposed to represent the area under a curve. If I compare that with my answer of negative 2, it doesn't make any sense. That means there's something wrong here. There's something we're not considering. So we're going to do this again more carefully and make sure that we're taking into account this part here in the middle, which is the vertical asymptote. So let's see what we should be doing. Forgive me, I had to find what I was looking for, so I needed to zoom out a little bit. All right. What's the right way to go about this integral? Well, let's get rid of this stuff here first, because that wasn't the right way to go. It didn't make sense. What do we want to do instead? Okay, well, we know the problem point here is going to be 2. And the reason we can tell that is that we have x minus 2 in the denominator, which tells us the integrand will not be continuous at x equals 2. That means that's exactly where we should be splitting up the integral. We should be making a similar situation as when we had that 1 over square root of x function being integrated from 0 to 1, except now we have an integral from 1 to a and an integral from b to 3, and we're letting a approach 2 from the left and letting b approach 2 from the right. So what that looks like is exactly this setup. Integral from 1 to a of our function, integral from b to 3 of our function. We've split it up into 2 completely separate pieces, and we're going to calculate each one separately. And if both of these end up being finite in the limit, then that means this area was in fact finite. But in reality, what's going to happen is there's going to be part of it, one or the other or both, that's going to be infinite. It's not going to converge. If we look at this calculation, that's what we'll notice. So because that's what happens, because one piece of this doesn't converge, it means the entire integral doesn't converge. We could do the other piece too, but it doesn't make much of a difference because we're going to still conclude that the whole integral diverges. All right, so that brings us to our summary. What does it mean for an integral to be improper? One way is you have an interval that's unbounded that you're integrating over. In other words, one or both of your limits of integration is plus or minus infinity. The other is if you have a vertical asymptote in the interval you're integrating over, or possibly at one of the endpoints. And why do we care about improper integrals? The example we talked about with call wait time and the light bulb example at the very beginning of the section, it's allowing us to calculate certain probabilities that involve infinite limits. We have to remember to treat an improper integral not like plugging the number infinity or negative infinity into some expression, because that never makes sense. Sometimes we play around with that intuitively, but it's actually not helpful because things can go wrong sometimes with that. So what we do to get around it is we make a limit of an integral. And then we figure out if the limit exists, the integral converges. If the limit doesn't exist, we say that the improper integral diverges. Now, you might not be aware yet why this is useful, this integral from 1 to infinity of 1 over x to the p dx, where p could be in one of these two categories, but you will see soon when we talk about series.